Good. So now, welcome to the last lecture on statistics for data science with the attendance that is, I guess, expected if the material is not really exam relevant and it's the last lecture. No, well, a few people may join. It's the last lecture and the topic today is variational inference. So this is our last lecture on Bayesian inference. So it's in this group of Bayesian inference where we first had an introduction to the essence of Bayesian inference, and then last week looked at numerical methods to perform Bayesian inference, and this week we are looking at an analytical semi-numerical, depends on whether if you use optimization methods you call that then numerical, but it's definitely not numerical in the sense of sampling. So a semi-analytical numerical methods for doing inference in probabilistic models, which also subsumes a lot of different forms of inference in general. So we wrote a paper in 2017 that formally shows that variational inference includes things like expectation maximization and maximum likelihood as special cases. That has been known, of course, before we wrote our paper, but we wrote it up in some formal form again. And so from my point of view, variational inference is kind of the most encompassing inference technique for probabilistic models. It doesn't require you to turn on a random number generator, but what it often requires you to turn on is some optimization toolbox. And variational inference is so it originated in the 90s. Of course, there are precursors in the literature that go back to earlier days. For example, expectation maximization had been around, of course, since the 70s. So the full development of this variational inference framework maybe only happened in the late 90s, early 2000s. And primarily in machine learning, in groups where people see themselves as machine learner who are interested in probabilistic models, and only slowly now makes its way actually in the into the statistics community, although it inherently is actually much more statistics, if you think of statistics as probabilistic modeling, than it is machine learning, if you think in machine learning as probability-free classification or something like that. And only in the last couple of years, actually, the statistical analysis of variational inference has really started. So looking at whether this is actually doing something sensible in the sense of, for example, frequentist estimator criteria. This is only now beginning. So it's a kind of state-of-the-art approach, in the sense that state-of-the-art always means that it's not that consolidated, not that clear, and a little bit confusing, although I think the lecture is not confusing, but state-of-the-art doesn't really mean that it's the best and the best to be understood. It just means that it's the latest shit, and that sometimes it's not that fully developed. So variational inference is definitely state of the art. I think you heard a little bit about variational inference in the a lecture on variational autoencoders. Like I mentioned, I think before, variational autoencoders is the name that was given to variational inference, which was developed during the 2000s, let's say. Then deep learning or neural networks came up again, and then some people, so this Kingma, they rediscovered that there's something called variational inference, and why not put a neural network, so a nonlinear function, so a linear nonlinear function, so the typical neural network concatenation that you all know, why not put this somewhere in variational inference and call it variational autoencoders, and then we get famous and everybody's talking about variational autoencoders, but that's just of course variational inference, with I think a likelihood function that is uses parameters that are reminiscent of hierarchical linear models, but maybe put some nonlinearities in there. In any case, we try to go a little bit more to the foundations and look at that. But I think also in your machine learning lecture, some of the foundations were covered, as I saw. So most of this is based on a tutorial that we wrote some time ago, where we applied or we looked at the use of variational inference for linear state space models, so for time series analysis. David Bly in the US has done nice groundwork for variational inference over the last 5 years, or maybe 10 years, including the publication delay that tries to popularize variational inference and tries to encourage statisticians, so people with proper formal training and not some random machine learners who like to implement but not to think about what they're implementing. So to motivate statisticians to look at variational inference, which is also important. So I fully agree with him there, because there is still a lot to be done and said. So if you look at David Bly's work, that's a good starting point. In neuroimaging, variational base has been around for longer, although maybe not necessarily in a better way. So Will Penny has made some contributions to variational inference in parametric models. Carl Friston, of course, used variational inference to build his great theory of everything on there, although that's mathematically sometimes not that clear. And we have also written more on that, for example, about variational inference and its special cases and its application in general linear models. I have a tendency to always look at the application of methods in simple cases. Everybody else feels better if they apply it to the most complex thing and then don't get quite clear, so I prefer to look at a simple thing and then try to get as clear as possible. In any case, that's variational inference, some literature remarks, and that's the plan for today. So we first want to look at the foundations of variational inference. This might overlap to some degree of what you heard in variational autoencoders, but that doesn't hurt. Once we looked at the foundations, we can look at two examples of variational inference, free from variational inference for Gaussian gammas models and fixed from variational inference for nonlinear Gaussian models. Like maximum likelihood or many of the big statistical ideas, variational inference, of course, is more a big idea rather than a concrete algorithm. It can, of course, for a given model, it can take the form of a concrete algorithm, but usually you have to work that out. And it's more a general spirit of how to do things rather than just one set of commands that then solve everything. Okay, then let's go and first look at some foundations of variational inference. So I start here with the definition of a variational inference problem. And this is essentially the Bayesian inference problem. So there is not really a big difference between saying I want to do Bayesian inference and I want to do variational inference. Variational inference is one approach how you can perform Bayesian inference, so quantifying uncertainty in probabilistic models. So we assume that we have a set of observable random variables, as always denoted by x1 to xn, and we have a set of latent random variables, z1 to zm, and these latent random variables, they can of course be parameters. So in Bayesian inference we of course model uncertainty over the parameter by conceiving the parameter of our model, not the true but unknown parameter, but the parameters in our probabilistic model as random variables. Of course, there are also other models where, for example, state space models, which we didn't cover this year, where you also have not directly observed random variables, which might follow some dynamics. So the specific thing about parameters is that they are constant for all or they are assumed to be constant for all observations of the data. Other latent random variables, for example, in state space models or hidden Markov models, they can of course also exhibit some dynamics. So here we basically consider both cases where the latent variables might have some conditional independence properties. That's the more general way to say that they have some dynamics, or so some specific conditional independence properties where you have some conditional distributions, or they are, and in this case you can of course also model them to be constant if the transition probability is always to stay on the same value. So everything is covered here, but instead of just saying we have parameters, we're saying we have latent random variables, and we assume that we have a probabilistic model of the typical Bayesian form. So we have a parametric, in this case parametric form, where we have p x z, so the joint density of x and z, to factor into a marginal distribution over z, so the latent random variables, and a conditional distribution over the observed random variables. So the typical Bayesian setup. What we then want to do with variational inference is to approximate the conditional distribution pz given x. So that's what we would call, if z would be parameters, we would call this the posterior. Pz would of course be the prior, and we would like to evaluate the log model evidence. So the log of the joint distribution over the observed and the unobserved random variables integrated with respect to the latent random variables. Of course, if we want the conditional distribution, we need this normalizing constant, not necessarily the log, but we need the normalizing constant, p of x. But as we've seen last time, there are, specifically in numerical methods, there are ways that you can get to the conditional distribution without ever evaluating the marginal marginal distribution, so the evidence. And that then means that, for example, in sampling methods, you end up, and that's actually quite common, you end up with the posterior distribution, and then you still have to find a way to figure out the log model evidence if you want to do model comparison. And variational inference does both things at the same time, so you get a quantification of your uncertainty over parameters or latent variables given observed variables, and you get an approximation of the model evidence as the marginal likelihood, so the joint distribution over observed and unobserved random variables integrated over unobserved random variables. And it's an approximation, so in general it's an approximation. Of course, in simple cases this can be also shown to be exact. So if you have things that you can solve analytically, like in the conjugate family, then of course in variational inference, if you apply the variational inference ideas, your approximation gets exact. But in other cases where you are where the analysis is not trivial, or maybe not even possible, then you get an approximation. And of course an important question for understanding and developing variational inference is to understand how good these approximations are, but that's not that far in the development of variational inference yet, I would say. Yeah, so that's the variational inference problem. So we have a probabilistic model with some latent variables, some observed variables. In the Bayesian scenario, latent variables would just be parameters, so the standard Bayesian scenario. We want to evaluate the conditional distribution of the latent random variables given the observed random variables, so the posterior, and we want to evaluate the marginal likelihood of the data, or its log, and that's the log model evidence approximation. Of course, conditional densities and marginal likelihoods are central in Bayesian inference, as we discussed in the first lecture on Bayesian inference. Variational inference is also known as variational Bayes, so I called variational inference for a long time variational Bayes, and only now started to call it variational inference because it's more the term that's becoming more popular. And then you, of course, also usually, I don't know how it is these days, but sometimes people might still have a problem with the term Bayes, but I think people don't have the problem with the term inference, especially in latent variable models. So even if you're a hardcore frequentist, you can appreciate that sometimes you have latent variables in models and then want to do inference on them. And because variational inference can do that, it makes sense to call this whole thing variational inference or variational inference and not variational based. But of course in the literature you find the term variational based a lot. As already explained, the latent variables may represent parameters or latent states, and in the applications you see that it's more common for pxy to be a density than a probability mass function. So the typical applications that you read about are with respect to PDFs, but there is no restriction really of variation inference to the density parametric case. But on the other hand, there's also not very much general formulation of variational Bayes. So we tried that in our 2016 paper a little bit. If you look into the supplement, there you find, if you want, measure theoretic or probability theoretic formulation of variational inference. But that's definitely not the standard way to how people talk about it, which of course also has to do with the fact that a lot of people, although they work in machine learning, of course they don't have a strong background in measure theoretic probability theory, which of course enables or allows to generalize things and can be done in variational inference, but that's not the main language to talk about that yet, mainly because a lot of this stuff also is then written by computer scientists. So how does it work? So that's what we want to discuss now. So one thing that is central to variational inference is the what I call log model evidence decomposition, and I guess more people call that the log model evidence decomposition. So we start out with the probabilistic model that we of course formulate, and we take another distribution QZ, which is a distribution over the latent random variables, and we call this variational distribution, and this will be our approximation to the posterior. So we're trying to approximate the posterior distribution by some other distribution, which we call variational distribution. It's called, of course, a distribution over the latent variables Z. And the whole thing works based on the fact that we can write the log model evidence, so the marginal likelihood of the observed random variables, as the sum of what is known as the evidence lower bound, which is a function of the variational distribution, and a KL divergence or the KL divergence between the variational distribution and the posterior distribution. And this log model evidence decomposition is not unique in the sense that you can also use different divergence measures between probability distributions, and then your evidence lower bound would look different if your divergence is actually has some properties, so that it's non-negative and a zero if these are the same. So this whole thing, variational inference, is not completely tightly linked to KL divergence measures. It's the most popular way to do that, but if you wanted to write a paper, and there are of course a couple of papers in this regard, how you can generalize this, then it's more important that you have a divergence measure and that you can evaluate a corresponding evidence lower bound. What are these things? So the evidence lower bound is a function of the variational distribution and takes on the following value. It takes on the integral over the latent random variables of the variational distribution times the log of the ratio of the joint distribution and the variational distribution. You can also view this as the expected value of the log of the joint minus the entropy of the or plus the entropy, that depends on the sign, of the variational distribution. Why this formula? This actually derives more from the fact that how you define the KL divergence and what remains. This elbow is known as the evidence lower bound. It's a function of QZ. And the other part here is the KL divergence, the Kullback-Leibler divergence between the variational distribution and the conditional distribution of the latent random variables given X. And that's defined as this. So we will look at both terms in more detail to get clear what the intuition is, but that's first kind of the theorem. So we can rewrite the log marginal likelihood as the sum of this term, which for the moment we call elbow, and the sum of this term, which we call KL divergence. These variational distributions, they might have parameters. So for example, if you choose not a fixed form variational inference, if you choose QZ to be of a specific parametric form, or in free form variational inference, if the form of QZ falls out of the framework, these distributions are often parameterized, and we call the parameters of these variational distributions variational parameters to clearly distinguish these parameters from, for example, the parameters of the probabilistic model P, or also of the posterior distribution. You might notice, but we will get to that, that we are trying to approximate PZ given X here, and we don't know it. Otherwise, we wouldn't need to do this whole thing. So that's why one often only deals with the elbow in variational inference. So one actually changes the elbow, as we will see, and not the KL divergence. So don't get confused that here that we have the conditional, although we do the whole thing because we don't know how to analytically evaluate it. It will work, as we will see in a second. The elbow, that's the kind of modern, more David Blei kind of term for this. It has long been known as the variational free energy, or free energy, and I strongly prefer the term elbow because it's an information theoretic or probability theoretic quantity that arises here in the context of probabilistic models. If you give it the term energy, then this derives from, of course, physics. Then everybody is confused and wants to link that to some notion of energy where people think that they know what energy is, and then it all gets horribly confusing. So the term elbow describes much clearer its role in variational inference, and then the elbow just has a definition, and there's no need to try to link this to where it's actually coming from, or what it has been inspired by, namely thermodynamics, so the mathematics of thermodynamics and statistical mechanics. That's all very interesting and has derived certain mathematical forms, but it's really not that crucial in this context of variational inference. Now, why does this hold? That's fairly straightforward to see. So if we define the elbow like this, then like we did here, then we can rewrite the joint distribution here as the marginal times the conditional of the latent variables given the observed random variables. Then we can use the properties of the logarithm and the integral to take these two things apart. We have here the integral over the latent variables, so p of x we can take out, then we can integrate out this, that's 1, and here we are left with the definition of the KL divergence. So it works because the elbow is defined like this. This gives us the log marginal likelihood and the KL divergence. Of course, you can also view it in a different way, that you need to find the elbow such that you end up with a divergence term here. So if you would use start with a different divergence term, then you could in principle define a different elbow such that again you get the log model evidence here, and then your different metric for comparing, or not necessarily metric because KL is not a metric, but a different metric for comparing probability distributions. So why this decomposition works is just because the definitions are like that. So that doesn't really explain what the whole thing is doing or what it's for. But before we can look at that, we need to look a little bit into the details of what these things actually are. So I don't think we have really covered KL divergences yet. So for two PDFs, QZ and PZ, the KL divergence QZ PZ is defined as the integral of the expectation of this log, the expectation of this log of QZ divided by PZ, or the integral of QZ times the log of QZ and PZ integrated over Z. And this divergence serves as a dissimilarity measure of QZ and PZ in the following sense. If PZ and QZ are not identical, then the KL divergence is larger than 0, and it gets larger if they are more different, which is then something one needs to specify, but one can easily observe in examples. And it's 0 if and only if QZ and PZ are identical. So it does not get negative, and if QZ and PZ are identical, then their dissimilarity is 0 because they're identical. If they are not identical, then the KL divergence is 0. It's not a metric. The KL damage per se is not a metric, so it doesn't fulfill the metric criteria, specifically not the triangle inequality. But you can create a metric from it by looking at both the KL divergence in the QZ and PZ direction and the PZ and the QZ direction. If you prefer to have a metric here, then I think you can still do variational inference. You need to specify your elbow a little bit different. I still think that would work. It's not the way that it's commonly discussed, and it works. So the standard way here is that it works like that. Having a proper metric, so a proper distance measure for the two distributions in variation inference would be interesting. I wonder whether there are any constraints, how well this then works and so on, but I think this has really not been explored systematically. We will look at the KL divergence in more detail in the Übung session today. So for now we just assume that these things hold. They are a consequence of Jensen's inequality, which we've seen earlier. So this is why we also try a little bit of a proof of Jensen's inequality, because in the end KL divergent properties follow from Jensen's inequality. The crucial thing here is that the KL divergence is non-negative, and that it's 0 for identical distributions. So here's an example to get an intuition about this. So this is comparing two univariate Gaussians, one that has parameters mu q and sigma square q, and one that has parameters mu p and sigma square p. I take one as the reference distribution that I don't change, and that's the Q distribution, or the mu Q and sigma square Q distribution that is set to the standard normal here, and this is shown here on these graphs as the blue. So you see that the blue univariate Gaussian is not changing, and then in this graph I look at different values for the parameters of the P distribution, one that is very close to the Q distribution, where you don't see much of a difference between the two probability density functions, and if you evaluate the corresponding KL divergence, you are here almost at the minimum of the KL divergence. Now if you for example change the expectation parameter of the one of the distributions with respect to the other, like here, then you increase the KL divergence. So here we have this mu parameter of almost here we have this mu parameter of almost 2, so the KL divergence increases a lot. The KL divergence also increases if you don't change the expectation parameter, but the variance parameter, it doesn't. So here from going from a variance of 1 to a variance of almost 2, so 1.8, doesn't change that much, but it still changes. So the KL divergence measures how different the two distributions are. Of course, then you can again, it's more of then a question of how you put your intuitions into mathematical formulas. If you have strong reasons to say, but this red here is more different to blue than this red here is different to blue, so I want a larger KL divergence for this difference than for this difference, then you can find some metric that gives you that, but the KL divergence has, or the KL divergence formalizes this or implements this, that this shift in means has the stronger effect than the shift in variance. And of course you can think more about why this may be good. So that's the KL divergence. We see more of that in the Übung. It's a difference measure between the between two distributions, and it's used in the variational inference framework as a difference measure between the variational distribution and the posterior distribution. Again, as we will see, the variational distribution we can modify, the posterior distribution we don't know, but of course what we will see is that we can minimize the KL divergence, and if the KL divergence is 0, then our variational distribution corresponds of course to our posterior distribution. But how do we do that? Well, we consider the elbow, hence more about the elbow now. The evidence lower bound is a lower bound of the log model evidence, so the elbow is always smaller or equal to the log of the marginal observed random variable's likelihood. Why is this the case? That follows directly from the fact that first we have this model evidence decomposition, and the fact that this is always larger or equal to 0. So this value must always be smaller, or if the KL divergence is 0, equal to the log marginal likelihood. So the lower bounding fact of the elbow follows directly from the properties of the KL divergence. This is why the non-negativity of the KL divergence is important for variational inference, and this is why Jensen's inequality is important for variational inference, because that's where the non-negativity of the KL divergence comes from. So some remarks for a fixed data set. So if we have observed some data, then of course the marginal likelihood is a fixed scalar quantity, and we can view it here maybe as this bar. So the length of the bar is thought to represent here the marginal likelihood, and then the evidence log evidence decomposition says that we can decompose that into a positive or non-negative part of the KL divergence, and the rest is the elbow. And this suggests two ways now to solve the variational inference of approximating both the posterior and the marginal likelihood. So one thing is we could minimize the KL divergence. So we could say, okay, we minimize this, then the elbow would correspond to our log marginal likelihood. In principle, we can do that, but the question is a little bit how we do that if we don't know pz given x, because that's what we're trying to approximate. The other way is that we maximize the elbow with respect to qz. If we make this elbow part here bigger and bigger and bigger, at the same time we make the KL divergence smaller and smaller and smaller, and if the elbow is minimized and the KL divergence vanishes, then the elbow of course corresponds to our log marginal likelihood, and because the KL divergence between the variational distribution and the posterior distribution is minimized, the variational distribution corresponds to the posterior distribution. And so the common way to do variational inference is to work with the elbow and maximize this with respect to the variational distribution, and do this usually numerical. Of course, in simple analytical examples you can also do that analytical, but if you use this in a numerical approach using some in some standard application, then you would try to maximize the elbow as far as possible, and then take the converged value of the elbow, the maximized value of the elbow, as your approximation of the log marginal likelihood, and the corresponding, because you maximize it with respect to this distribution, the distribution, the variational distribution at convergence of your elbow to the maximum value as your approximation to the posterior. Yeah, so variational inference typically follows the latter approach. Now, to do so and to do variational inference, there are often some simplifications invoked with respect to the variational distributions. They are not completely necessary, and if you look into the literature you will find nowadays papers that say how to do variational inference without mean field approximations. On the other hand, if you look into the applied world, and if you really want to use this on first instance, then these simplifications like the mean field approximation make sense. And if you want to kind of have even more general approach, then this is also a starting point where you maybe want to loosen some constraints. So so for now I discuss mean field approximation as kind of integral to the variational inference method to get started. So what does it mean? One could also call that differently. I think this mean field term is still like variational free energy, still derived from these physics precursors and intuitions. One could also call this independence property of the variational distribution, or partitioning of the variational distribution, which would describe it a little bit clearer in probabilistic terms. Because what it means is the following: we assume that we have a set of latent random variables of our probabilistic models, and we assume that we can partition this into mutually exclusive subsets. So we summarize our unobservable random variables into some sets from S1 to S. Not a nice abbreviation, which are non-overlapping, and which together give us our complete set. Of course, the easiest way to do that is to fully partition this and consider only individual random variables rather than subsets of latent random variables. The assumption, the mean field approximation, then means that we assume that that we build in a factorization property over subsets of these latent random variables. So we assume that we make the basic assumption about our variational distribution that it fulfills some independence properties, so that we can write the joint distribution QZ, the joint variational distribution, as the product of s marginal distributions. So QZSI, which is are the elements of ZSI, which is the subset of variables. So the easiest way to think about this, so the check the indices and so on, but the easiest way to think about it is you have three latent random variables and you assume independence of these random variables. So you factorize your variational distribution of Z1, Z2 and Z3 into the product of a variational distribution over Z1, 1 over Z2 and 1 over Z3. So like the independence property in that we, although it's completely different and with regards to latent parameters, but yeah, similar to the independence property that we always use for observed data. But of course here it's completely different because it's for latent variables, but the independence is the same. If one invokes such a mean field approximation, then one calls this mean field variational inference. And yeah, as I said, a common way to do variation inference is to to assume full factorization. One thing that one needs for fixed form variational inference is at least a binary factorization, so that you have one set of latent random variables that you assume to be independent from the other set of random variables. This often, if you, for example, do use this for parameter inference and latent variable inference in dynamic models, then a natural factorization is that you assume the parameters are independent from the values of your latent dynamic variables, and you factorize over those. If you have just two parameters, then this binary factorization is also trivial, but it's, as we will see, is necessary for what the free-form variational inference has in mind. Of course, what this means is that if you assume this factorization, is that you may have stochastic dependencies in your conditional distribution of z given x in your probabilistic models, but you neglect those. So if you think more about it, you can, for example, think of a bivariate Gaussian that might be your posterior distribution over z given the observed data, which has some, for example, dependence, so it's an ellipse. And if you approximate this now by an independent distribution, you approximate it by a circle. That's what's happening, and then of course one can study how good this is, and can look at things where one doesn't want this and so on, and try to do away with this mean field approximation, but the typical way is to do that. Yeah, I think it's a good time for a break now. Because this is kind of now all the background that we need, and with this background we can actually now look at a way to do variational inference. The first way to do variational inference, which is a free-form mean field variational inference, and this is what we will look at here. And then we can look at Carvey. And then we will look at fixed form variational inference, and I think we just leave that for after the break. So again, crucial is the log model evidence log model evidence decomposition, and then the fact that we work with the elbow. How exactly, this we will see when we talk about the free-form and fixed-form variational inference. And a common assumption to get fixed-form and free-form running is to do this mean field approximation. Are there any questions right now? Okay, then let's take a break and continue at 8:30. Okay, then let us continue for the final hour of the Statistics for Data Science lecture. We are in the process of discussing variational inference, and yeah, we established that what we want to do is to, let's briefly look over that again. We want to approximate the conditional distribution in a probabilistic model and the log marginal likelihood, and we've seen so far that we can decompose the log marginal likelihood into an evidence lower bound and a KL divergence, which just works by the definitions of the elbow and the KL divergence, and we've seen that the KL divergence measures the divergence between two probability density functions, or probability distributions more generally, such that it's 0 if they are identical and larger than 0 if they are not identical and become more different. This implies that the elbow is always equal to or smaller than the log marginal likelihood, and we have now the principal idea that we want to maximize the elbow with respect to this variational distribution to approximate the log marginal likelihood by the elbow, and use the variational distribution as the approximation for the posterior distribution or the conditional of the latent random variables given the observed random variables. And we established that to simplify proceedings, we assume some independence properties in the variational distribution. And then there are in principle two approaches to variational inference. One is the more analytical approach that is known as free-form mean field variational inference, and one is the more numerical optimization based approach that is called fixed form. We start with the free form, which is kind of also more close to the origins of variational inference in physics. So we assume that we have a probabilistic model, Pxz, comprising, as stated in the beginning, observable random variables x1 to xn and latent random variables z1 to zm. We assume that we have a variational distribution that we of course make up, which may have some sorry, no, that's I shouldn't say that. I always say that, but it's not necessary here. We just assume that we have a variational distribution and that this factorizes, but we don't specify any functional form of this. So we just assume that there is this distribution with a density that we can write as a density over S of our of the random variables in a set S, and the remaining random variables. Then setting Q of Zs to 1 over a normalization constant times the exponential of the integral of the log joint density multiplied by the density of the complement of our Zs. So for example, if we just have two latent random variables, this would be our variational distribution over Z1. That would be given as this integral with the second random variable in there, but more generally a set of random variables, and Z without S being the complement of Zs with respect to our set of random variables. Then setting the variational distribution over the random variables Zs to this maximizes the evidence lower bound. So if you want to, so what this says is, if you want to maximize the elbow with respect to the random the variational marginal distribution over these S random variables, then you should set it to this exponential of this integral, or the exponential of this expectation. Of course, this is the expectation of the log joint density under the other or the complementary set of latent variables. And if you can do that for ZS, then of course you can just change the notation and consider Z without S here, and Z with S here, and Z with S here, and then you have how you can maximize with respect to the other set of variables. So again, the simplest case is that you have two sets of variables, maybe even just two latent variables, and then you get QZ1 by evaluating this here for your current setting of QZ2, and then afterwards you set QZ2 and evaluate this with respect to your current setting of QZ1. So this would then be called a coordinate-wise elbow maximization approach, because your elbow is a function of your distribution of all latent variables, and you consider the variational distribution of a subset of random variables at a time to maximize the elbow. The point and why this is called freeform here is that the functional form of QZS depends on what's actually happening here. So you need to do this analytically. You don't assume a specific functional form for the variational distribution beforehand. You evaluate it and then you get the functional form. And that's different from the fixed form approach. Why does this work? This works because so there are different ways to show why this works. One can show this based on variational calculus. So you might know what variational calculus is. So in standard calculus, you can maximize or optimize functions with respect to numbers or vectors. In variational calculus, you optimize functions with respect to functions. So of course, probability distributions and probability and the corresponding probability density functions and probability mass functions are functions, and the elbow and the KL divergence they are also functions in the modern nomenclature. In the old school nomenclature, they are functionals because they are functions of functions, and hence if you want to maximize some functional, so the elbow, which is a function of a probability density function, then you need variational calculus, and you can do this based on variational calculus and show that this result holds. This is what we did in our tutorial. Of course, this also had been shown before, but we basically go into the details of variational calculus and how this then actually looks. There's another way to show that which doesn't require variational calculus, and that's here. That works essentially by showing that one can rewrite the elbow as the negative KL divergence between the variational distribution over this one subset of latent variables and the the right-hand side here of our freeform mean field variational inference theorem minus some constant that doesn't depend on QZS. So then, of course, if this is the case, then of course we can maximize the elbow by minimizing the KL divergence, because we have this negative sign here. So if we want to maximize this, we need to minimize this KL divergence term, and of course we can minimize this KL divergence term by setting QZS exactly to this, and then we maximize the elbow. So this by showing that the elbow can be written as minus KL minus this KL divergence, we then already have that we can maximize the elbow by setting QZS as explained here. The other way to show this is by using variational calculus and setting the variational derivative of the elbow to 0 and then solving like you would do in standard calculus. So that's what I said, maximizing this negative KL divergence by minimizing. Awesome. Minimizing this negative KL divergence or maximizing this negative KL divergence. Yeah, that so you minimize the KL divergence, but you maximize the negative KL divergence. Maybe let's then remove this because we maximize a negative KL divergence by minimizing the KL divergence here maximizes the elbow. And sometimes I can't really decide whether I want a comma here or not. So there are two ways to see this. You could either view the elbow as a function of QZS and QZ without S, or you see the elbow as a function of the mean field approximation. That depends a little bit on the view. As you might have noticed, I don't give functional or function definitions of elbow and KL divergence, because that would mean that I have to specify the space of the distributions here, and yeah, then there would be some space of distributions, which one can do, but it's not really like a nice space with, or of course one can establish this, but that would then really go into functional analysis, which we don't want to do here, so I avoid this by never really talking about the function definition of the elbow. In any case, don't worry if you see a comma here or not, that I think I haven't fully decided. For consistency, it would be nice to have a comma here, because there's a comma and there's a comma. So I'm viewing the elbow here as a function of two arguments, and that first argument is QZS and the second argument is QZ without S. Now, why does this hold? Well, this is just a matter of reformulating the elbow. I don't want to go over this now. I mean, it's in the end, it's is there a trick somewhere? I don't think there's much of a trick somewhere. It's just writing out logarithms respecting the linearity properties of integrals, and collecting things that don't depend on QZS in a constant. It goes a little bit on and on. Yeah, the exponential comes in because at one point there you need another log, and then you need another exponential because you don't have a log here. But in the end, you end up with this KL divergence. So, and the constants are actually listed here. So that's in a way a straightforward proof, but that's definitely a comma too many. That's a straightforward proof to show that this actually maximizes the elbow. Like I said, one can also show this via variational calculus. In the end, it's nice, but it also, for a given example, gives you just an ansatz or an approach now to implement a free-form variational inference approach, because you still need to look at these integrals and look at your probabilistic model to evaluate this. Yeah, so it requires, if you apply this, this can be applied in relatively low complexity examples where you can evaluate all these integrals, and I have one example that we can maybe briefly look at the end of the lecture, and then also in the Übung. That is this Gaussian gamma model, where you have what do we actually have? Yeah, you have a gamma distribution over the variance parameter of a univariate Gaussian, and you have a Gaussian over the expectation parameter of the Gaussian, and you have a scenario where actually an analytical solution is not possible. Then you can develop a variational inference approach based on this freeform variational inference setting, but you need to do all the analysis, and in the last evaluate the integrals analytically. And if you at one point figure out you cannot do this analytically, then you need to use approximations. In the last 10 years or so, maybe there is, of course, because doing this analysis can be quite tedious, and of course you can make mistakes. In the end, you have a nice analytical solution, and if you study that it's actually working, then you can be happy. But of course, machine learning, big data people rather want to not do that much analysis and it's tedious and so on. So there are also other approaches to do this. So there's also this combination with MC techniques, which I'm not really into, so I don't know exactly how it works, but that gets around some of these analytical steps in freeform mean field variational inference. There is, we are not quite done. These two, or at least this insight, so that there is a freeform variational inference, this then implies, as I hinted already at, a coordinate ascent variational inference approach. So there you have a probabilistic model, you have your observable random variables, your latent random variables, you have factorized variational distribution, and then based on the fact that this formula that I showed you there maximizes the elbow with respect to one coordinate, then you can formulate the following coordinate ascent variational inference algorithm, and this coordinate ascent variational inference is then also known as CAVI. You need to initialize your variational distributions. For example, you can set them to the respective priors. To respective priors, and you marginalize over the other distribution, and then you evaluate the elbow based on your initialization, and you select a convergence criterion, and then you keep on monitoring the elbow for your updated elbow value, and check whether this is larger than your non-updated elbow value. And on each iteration of the algorithm, you set your I+1 iteration for your distribution over QZ to exactly what we saw in the theorem, and then you plug your updated variational distribution into the formula for the complementary set of latent random variables, and then after you updated both of your variational distribution, you check the elbow again. Yeah, so this is already what I hinted at here. It's just written up once more. So this initialization, that's always a little bit confusing. So what in freeform variational inference, because you in principle don't need to assume anything before you do the first iteration, but you need to somehow evaluate this integral. So it turns actually out, if you do that in an example, so in this typical Gaussian gamma example, you don't require the parametric form of QZ given S when you evaluate this. So you don't need to assume that this is of a specific parametric form to get the functional form of your normal distribution, of your variational distribution here, which then is a normal distribution, and the same for if you look at the other distribution. So the functional forms you definitely don't need to build in this framework, because the first thing you do is in any case start here. It may make sense to monitor this based on the or to start with the actual prior, so to see whether actually you are only increasing, whether your prior is actually in some way close to your posterior already, but often what you actually find is what you do is that if you start from your prior and do your first update that doesn't depend on the prior, then this first update actually going from the prior to your first variational distribution, so going on iteration 0 here, actually decreases the variational free energy or the elbow. So it's not it's not really part of the framework. It's I'm a little bit interested in also this first step, so why or what's happening there. But the guarantees for this to work and for this to always increase the variational not the elbow, not the variational free energy, the elbow, they start really from the first time that you set qi plus 1 and q over zs and qi plus 1 over z without s. So this here is not, so I always have this in mind, because this is always something that you definitely have to do in fixed form variational inference, but here you might as well not do it and just get started here. So yeah, in a way maybe one should take this out, but then one also does not really a starting point here. Naja, in the end this converges hopefully, and what you then use as your posterior distribution is the product of your two converged variational distribution, and as approximation of the log marginal likelihood you use the value of the converged elbow. So here's a visualization. So before going through the iterations, things look like this, and then the first thing you do is update qz over zs. This increases the elbow, and hence, because the length of this entire bar is fixed, decreases the KL divergence, and then the elbow is increased again if you update the z without s part, and the KL divergence is decreased again. And this you then do until convergence. You don't really have a good guarantee that in the end because this whole thing is of course meant to be the log marginal likelihood, you don't have any guarantee that the KL divergence at the end is 0 or something like that. This happens in cases where you can actually evaluate the posterior distribution and use this approach. So if you look at a special case like what actually scenarios where you have analytical solutions available anyway, so in conjugate Bayesian scenarios, and you play through this variational inference scenario, then you end up with a 0 KL divergence, and your elbow actually corresponding to a log marginal likelihood, which you can of course also directly evaluate. But in general, there's also so far not really a good understanding of how close your elbow then is to the true log marginal likelihood. So there's again more work to be done. So that's freeform variational calculus, and that's maybe a little bit like conjugate Bayesian inference or analytical maximum likelihood. So it works in textbook low-key examples. It requires some analysis, but if you're clear on the math, then the result is relatively clear, and it works, but it doesn't generalize well to everything that you might want to do. And hence there are other variants of variational inference that have more this kind of generalization property in mind, so things that make your life analytically easier. And one form is fixed form variational inference, and the key thing in fixed form variational inference is that you make an assumption about the parametric form of the variational distribution. So you might also use some mean field approximation, but you definitely assume that your variational distributions are of a specific parametric form. So for example, you don't do this here where you evaluate an integral and then wait for the functional form of the parametric distribution to fall out of the framework, but you specify that your variational distributions, for example, are Gaussians. So you say, okay, our variational distributions are Gaussians. And then if you assume that you have a specific parametric form for your variational distribution, then you can of course analytically evaluate or at least analytically approximate. For example, in a typical example, you use a Taylor approximation of the probability density function here. There are different ways to view that, blah blah blah. But you need what you can do, because you know both the functional form of the variational distribution and you know the functional form of your probabilistic model, which you define in the beginning. You can evaluate the elbow, or at least analytically approximate it. And then the elbow becomes a function of the parameters of your variational distribution. So it doesn't become, so it's not any longer a function of a probability density function or probability mass function, but it's a function of parameters, so vectors, numbers, and you have a multivariate real-valued function. You then turn your functional optimization problem or your variational calculus problem into a standard multivariate calculus optimization problem. So your elbow is just a function of the parameters of the variational distribution. It gives you back one value, namely this elbow value, and you try to maximize this function with respect to the parameters. So you're in a typical numerical optimization scenario. And then, if you maximize this, this then maximizes, of course, the evidence lower bound. And one example for this is, as I already said, that you assume that the variational distribution is, for example, a multivariate Gaussian. Using Gaussian distributions here as variational distributions is by some people called variational Laplace. Makes it horribly intertwined with the Laplace approximation without making really clear what the connection is. So I don't find it too helpful to call this variational Laplace. Maybe if you can spell out what this has to do with the Laplace approximation in math, then I'm happy to call it variational Laplace, but otherwise it's a little bit confusing. It's better called fixed form variational inference using Gaussian variational distributions or something. In any case, you then have a optimization problem which is still not simple, because you optimize your function. Your elbow function is then a function. It's a multivariate function of a vector and a covariance matrix, and so you're in full matrix differential calculus. So you better read the Magnus Neudegger book, what it means to maximize with respect to matrices, which actually have some constraints here, because your covariance matrix, of course, cannot be any matrix. So you cannot just add something to your matrix, but you must make sure, so you have a constraint optimization problem, because you need to make sure that your covariance matrix remains positive definite. And then you can look into information geometry to make sure that this is fulfilled. So it's still not easy, but at least you got from doing a lot of analysis in the freeform scenario, you got to something that is of general character, because you have a general numerical optimization problem where, of course, a lot of people have thought about. Okay, so the rest would then be looking at examples. Yeah, I think it would make more sense to look at the examples actually in the exercise session. So we will first, in the exercise session, deal with the general variational inference properties again, and then I show you an example variational inference approach for this Gaussian gamma model, and I think it makes more sense to show you the math of the variational inference Gaussian gamma model then, rather than to show it now. Because in the end it's just this algorithm that is implemented, and I can show you how this looks in computer code. So my suggestion is, or I decide that we stop here. So you have now heard an introduction to variational inference. You haven't really seen it in action, but that's at least, or you haven't seen any form in action, but we will see the free form in action this afternoon. But we will stop here. So that was an introduction to variational inference. Are there any questions right now? Okay, apparently not. Then let's start again at 1 p.m. today. Listen to the final presentations, look at an example for variational inference, and then if there are any, address any questions regarding the exams, which will happen then 2 weeks from now, the first date. Because today is then also the last day to ask content-related questions regarding the exams, and I will send around an email with the final exam qualifications, so when the exams happen and so on, possibly early next week or so, because it's only at the 12th of March, so there's still 2 weeks time, and maybe people have thoughts about taking the exam on one or the other date still. Okay, then let's stop with the lecture for today and discuss examples and a little bit more foundations then today at 1 p.m. Goodbye, see you at